Hello, everyone. We will get started in just about a minute and a half. I just want to make sure we give time for other people to join. Welcome, welcome. Okay, we are at 3 minutes past the hour, so I'm going to go ahead and get started. We will have people still trickling in over time. So you might hear me repeating a couple of things just to make sure that everybody gets the message about what's going on for today in our session. Thank you all for coming today to Outco's Visitor Class session. So the way that this is going to work is this is going to be a sample of what a typical technical class would look like at Outco. But before I get into all that, I just want to introduce myself because I know you should probably know who you're talking to, maybe a little bit of background about myself so that, you have something to relate to. My name is Karan Suraj. I am one of the technical instructors and software engineers at Outco. And I know a lot of people have a lot of varied backgrounds. I think some of you have actually come to my sessions or these sessions before. So welcome back if you're here for the second time. If not, just to give a little bit of some information about myself, I don't have a typical background. And I know a lot of you might not necessarily have your own typical backgrounds when it comes to being in tech. I started off as a chemical engineer. I'd always had a passion for tech, but I managed to make my way into the industry working as a BI developer and as a systems and platform engineer, deploying web applications, and also as a software engineer. And of course, because of my passion for tech, I decided to also get my master's in computer science. So I got pretty invested in trying to get through the ins and outs of the industry in tech and different roles, different perspectives, all those kinds of things. And one of the things that I'm sure a lot of you can relate to, regardless of your experience level, whether you're fresh out of college or fresh out of a boot camp, or maybe you have many years of experience, a couple of decades or something like that, is that the software engineering interview process can be kind of unforgiving in a lot of ways. There's a lot of technical things that you need to be able to approach in a certain kind of way, or maybe you're very savvy in the technical concepts. You can solve 100, 200 different leak code problems, a lot of them possibly even medium, some hard or something like that. If you don't know about leak code, it's just one of the practice mediums that you would attempt problems that you would commonly see in technical interviews. But you might be confident in that area, and but you might struggle in the behavioral side of things. So um, there's so many things, so many different avenues that you need to sort of think about when it comes to this process. And all of us have areas that we can improve upon. And that's basically the aim of what Outco strives to do when it comes to either the technical aspects of things or the behavioral career aspects of things. We help you see those blind spots to get through it. But today we'll just be focusing on giving you a sample of what the technical side of things would look like in terms of the instruction that we give, and the topics that how we might discuss the topics and approach them with you if you are going to sign on with us and and join our program. So the structure of the technical class typically would involve 3 segments. One is what we like to call a target practice session, where you work on a problem associated with the topic of the day, and you would typically work on it with a partner. and you put your best effort forward trying to communicate your algorithmic thought process in solving those kinds of problems or that particular problem in general. And then afterwards, you'd have an instructor like myself that would run through that problem and have you think about that class of problems. Say if it's about trees or recursion or some other data structure or something like, or algorithm that you might be thinking of. So that initial target practice segment, a solution lecture, those are the only two things that we'll be doing today. But in a typical class, we would also have a third component, which would be you doing mock interviews to actually practice doing interviews with that style, with that particular category of problems. And you'd be doing that with another peer or something like that. But again, we will not be doing mock interviews today. We'll just be having you work on a problem, and I will discuss that problem with you all when you have had a chance to attempt it. But you will also not be pairing off to work on the problem. You'll just be working on it by yourselves, and it will be given to you in the form of a HackerRank challenge. You'll have about 30 minutes on the timer to work on it. I will give everyone until 45 minutes past the hour for folks that will be starting late. If I do notice that everyone has completed it before then, I will bring everybody back, but otherwise, feel free to take a break up until that point. Okay, you know that was a bit of a mouthful. There's a lot more things, information I'm sure you're curious and about with regards to Outco or maybe what's going on. Feel free to ask any questions. Is there anything that I can clarify or any questions that anybody has? Okay, I think we have a couple of people that are joining in. Okay, so for the folks that have just joined, basically what we'll be doing is you'll be working on a challenge for the next about 30 or so minutes, and we'll come back and discuss this challenge. This is going to be a sample technical class that you'll be seeing. So I'm going to put a link to the challenge, a little bit more of an intro for those that are just arriving, and you all can get started. And if there are any questions, please drop them in the chat. Don't necessarily say them out loud because I want to make sure that people have the opportunity to concentrate without having too much background noise. So keep yourselves muted up until the time that we come back. All right. I'll see you all at roughly 45 minutes past the hour. Best of luck. Okay, let's go ahead and come on back. So the whole rationale behind starting to use recursion as a tool for something like this is that we're performing a set of repetitive actions that we're working with, right? So and they're arbitrary in nature, right? We're performing these three actions repetitively, and they're going to result in kind of variable conditions as we're going through this, right? My tree isn't necessarily some sort of this tree of possibilities that I defined, that I'm just drawing out for visualization's sake. I'm not actually producing a tree. I'm just showing this because this is a process of diagramming what we're working with. I am not necessarily going to have like a lot of balanced situations when I'm getting towards my result, right? There's going to be different stopping conditions at different points because I'm going to reach one as I go through these repetitive operations at different numbers of steps. Trying to do this with a while loop or a for loop is not necessarily going to be very easy. So I'm just using recursion because it's going to be a quick tool to hit the ground running, to actually just get something working that will use function calls as my repetitive operation to work through things. Okay, I see, Shirley, you had a couple things that you mentioned. If we have mod 3 equals to 0, we can start dividing by 3 to the n. I am not sure what you mean by dividing by 3 to the n.
Where like n would be 1 for the first one, and then 2, like see how many times you can divide by 3 basically.
Okay. Oh, I see what you're saying. So you're okay. So you're looking at some kind of implicit divisibility in terms of like the number of threes that are going to be apparent, like if you repeatedly divided by 3, if you actually got to a number that actually was finally divisible by 3, like all the possibilities in between.
Yeah.
I
So like that's why I was saying the 6, 3, and 2. So like if it's divisible by 6, it's divisible by 3 and 2. And so
okay. Okay, I see where you're going with that. And I see how that could possibly give you a route to try and come up with some sorts of optimizations. The only caveat that I have behind doing something like that is that you're still trying to find like a mathematical optimization that may possibly have some gaps in it for some certain scenarios. I'm not going to say that it won't necessarily work. I'm just going to say that it's going to be hard to try and come up with something like that, and you may not necessarily pass all of your test cases when trying to come up with something like that.
yeah,
And
it's a lot of conditionals. So
it's a lot of conditionals, right? Yeah. So I'm not going to say it's not going to work. There are probably a variety of other approaches to solving this kind of problem, but we're not trying to like get towards like trying to figure out some magical approach. We're just trying to use a basic set of tools that you would normally think about using when you're coming to working in these interviews, unless you happen to be in a securities interview where a security role interview where finding some mathematical tools or knowing some math in an extensive way is going to be useful for you. And a lot of interviews, you shouldn't have to focus on that quite as much. But I understand where you're going. That's we're just we're just going to focus on the recursive approach for now. But by all means, give that a shot. Let's see if you can manage to come up with something maybe after this session.
So I had a similar approach using modulus, thinking that if I could divide by 3, then I get the biggest chunk taken away.
Mm-hmm.
But then you run into where it's 10, and it wouldn't work with 10. It would work with 5, but it wouldn't work with 10. And you're saying there's not this magical mathematical approach.
Mm-hmm.
How did you arrive to that? Was it just by sitting down and working through examples first?
Yep, pretty much. Yeah. You try smaller examples and then you build upon it with larger and larger examples. And when you start to see just the initial logic breaking on at least, or that idea breaking on like one scenario, then, you know, it becomes impractical to try and find every scenario where you can come up with some conditional to deal with everything. So that's where I decided to take a simpler approach, which is simply just explore all possibilities. And then what we can do is we could see if there's a way to optimize on top of that. So that's why I'm making use of recursion as a tool. I'm just starting from 10. I'm trying to either subtract 1, divide by 2, or divide by 3, wherever any of the operations are going to be possible, and until I happen to reach 1. And I'll count the steps along the way with each path. So there's 2 things that I started writing out some things, but there's 2 things that I want you all to let me know. With keeping recursion in mind as the tool that I'm trying to just start showing this brute force solution, what are 2 things that I might need when I'm employing recursion? Just as a basic definition of a recursive algorithm for this problem.
previous result.
The previous result, you mean like so for example, for 2, whatever we happen to calculate at these levels or something like that?
Or the next result, like it would be calling the same function on the transformation you're doing, like call it again divided by 3 or something.
Right. Okay. I think probably you might have been thinking about the same things. So Tung is mentioning base case, and Tarek, are you mentioning instance variables? Yeah, those are all going to come into play. I'm just going to mention at a high level that we're going to talk about base cases, and we're going to talk about the recursive relation or operations that I think it was Hunter, was it, or Andrew? I don't know which of you actually just mentioned the calling it on itself thing. I wasn't looking at the screen when one of you talked.
It's Andrew.
Okay. Yeah, so we'll have our recursive operations and we'll have our base case that we are going to actually terminate your recursive operations at. So first things first, I want to define just my base case, which is going to be the simplest possible input for this problem, what would be my base case for this problem?
The input is 1, and then
Okay.
it just gets 0 steps to 1.
Right. Right, because if we have an input of 1, then the output for the minimum number of steps to 1 would be 0, because there are no steps that we need to take. We're already there. We know exactly what to expect with an input of 1. With a base case, we can build upon this the recursive operations that we're going to, employ. So I know, Andrew, you mentioned that what we'll do is perform the operations that we need to do. There's 3 recursive calls that we would make where they're going to be possible. Right? We can explore all of these. And we're not quite done here, so let's actually just explore what we'll do with a small example. So let's start with 2. So you said that we return 0 for both of our base cases over here, right? Our recursive function calls should inevitably return an integer of some kind. So if I have n equal to 2 over here, that's going to mean that when I call on n minus 1, that should return 0. When I call on n divided by 2, that should return 0. And you know what? Let's write this here. And I think for the benefit of everybody, I'm just going to quickly take some time to just write out in the tree above all of the routes that are being taken with the operations that are being done, just because, just to make sense of this visualization. Okay, so. Okay. All right. Okay. Yeah, so we have all those operations. I'm showing what's happening with each branch that we're going to be taking. Now, the next question I have is of course, we can't necessarily take this one because we're not divisible by 3. What can we do with the integer results that are returned from these 3 function calls?
You can loop them into one, I guess, conditional.
One conditional,
Yeah.
but we have to choose one of them, right? Basically.
Yeah, you have to pick the min essentially, and also you can choose whether just to test on 2 or 3 because nothing's divisible by both 2. Well, yeah. If it's divisible by 3, it can be divisible by 2 also. But yeah, so you need to do 3 tests and do the min.
But I was thinking, like, if the result is 1, 2, or 3, if the result is 2 or 3, then it's the same condition. Like, if you're one step away from.
You mean like we're one step away from 1 or something like that? Of course, in this scenario, we're not even going to have divide by 3 as an option. So really, we're just selecting between 2 things that are going to return some value. So we will actually, we'll select between these 3. But what we're going to do is we're not necessarily going to select, like if we have both divide by 2 and divide by 3 possible, we're not just going to automatically just select the divide by 3 option over the divide by 2 option, because there might be some hidden information that we're not necessarily accounted for. There's so many different possibilities that happen down in the tree that you can't necessarily just think about with an immediate division. So just take all the information that you're going to be given, if it's going to be possible, and just take the minimum of those 3 integer results, whatever results happen to be returned in those scenarios. You don't want to try and mathematically optimize in the situation. We're just taking what we're given and taking the minimum of those paths so far. So let's just go ahead and get one thing out of the way. The result of what we're returning from these function calls is the minimum number of steps that it takes to get to from that particular input to 1. Right. So when I make this call right now, because what's happening right now is I'm calling recurse of 2. And what will happen when I do recursive 2 is it will basically attempt to consider these 3 options wherever they're going to be possible. And then we'll take the minimum of all of those steps. And we'll choose one pathway. And that will be used to define the minimum number of steps from 2 to 1. My input was 2, so I need to find the minimum number of steps from 2 to 1 in this particular case. So if I took the minimum of these 3 paths over here, what should I do with that information? I've already selected some path, but I should do something with that integer result.
I mean, pass it back up to the calling function.
Mm-hmm. Okay, and that's just going to be 0, right? The minimum of 0 and 0 is just 0.
Yeah. I mean, it becomes meaningful if you get further down the stack.
Right. It does become meaningful, but the main thing that I'm just trying to say is that, you know, we need to actually acknowledge the act of taking these steps, right? If I, what was that? Increment something?
Yeah.
Yep. So what we could do is we could just do this 1 plus, right? That's going to be our increment.
Oh, yeah, that's true.
Right? So the number of steps that we took to get to this destination, that's fine. Now we need to count this act of choosing to subtract 1. Okay, that step itself is going to be an additional step. Any of these 3 steps that we choose is going to be an additional step. So we'll say, okay, that operation is going to be 1 additional one. So we'll do 1 plus any of those lower operations, and that's going to get us a result of 1 over here. So this is probably the hardest part of this problem, trying to rationalize this 1 plus operation, but that's why I'm building it from the smallest examples that I can think about. And then you could start to make sense about how to refine your recursive algorithm, and then try even larger examples and see if it makes sense. For example, if I go ahead and replace this with 3, then,
so the best way to approach this would have been test driven.
in a sense, yeah. That's the main thing that I would basically stress when it comes to thinking about your algorithmic problem solving process. Try examples, see where they break and where they don't break, and if your thought process happens to work, then you can move forward with defining a set of steps for your algorithm that you're going to be working with. So let's make sure that it makes sense for 3. We can see for the result for n-1, that's this pathway right here. Let me write this out. Let's choosing this. For n divided by 3, that's this pathway right here. And for the n-1 pathway, we return 1. That's this right here. For the n divided by 3 pathway, we return 0. So we can go ahead and return 0 here. And when we take the minimum between 1 and 0, that's just going to be 0. And so we can just add 1 onto that, and that'll get the result for 3 to the input of 3 to be 1. And that makes sense for us, right? Because when you're given an input of 3, you can just divide by 3 and get towards 1, and that'll just be a single step that you need to take. So this algorithm works out for us, and we've refined it in such a way that it will do what we need to do. Let's go ahead and translate this into code. I know this isn't necessarily an optimized approach, but the point is that you're making something that works, right? Before, we didn't have something that applied that happened to work for our problem. Having a working solution is important. So let's go ahead and write this out. So I have an input of n. Let's call it on the outside. Right? It's often going to be a trap, right? When you are going to be in interviews and your interviewer is going to be like, how do you solve this problem? And you can't even suggest a brute force solution. That even if you might have it potentially on the top of your head, just explore all the possibilities. Then that's going to probably set you back a little bit. So at least come up with something basic, right? Think about how you might just try out everything and get towards your solution instead of trying to figure out like the best, most optimal way right off the bat, unless you have a clear picture of what you might do. I'm creating a nested function just to do my operations because it'll help me discuss the optimizations that I'm going to do. So first thing is, chronologically, we'll define our base cases. If we have any, if we have more than one, we'll have our recursive operations. And the last thing is, of course, what I told you, which was we want to return the minimum number of steps from our input to 1. Okay, so let's go ahead and write these up. We said if our input is equal to 1, then we're just going to return 0. And we have 3 operations that we could take. We can either subtract 1, divide by 2 or divide by 3. Okay, so I'm going to go ahead and just call make my first function call, which is going to be on my input -1. And before I actually get into the step of doing the divide by 2 and divide by 3 operations, I'm just going to return what it's going to look like if we just attempt to just take one single pathway. This is me basically saying that I only am going to just look at this particular path in my tree right now, just that path. So if I run this, I should get 9 as a result, because if I'm subtracting 1 repeatedly, there's literally just 9 steps that you can take to get from 10 to 1. Okay, so let's go ahead and do the divide by 2 and divide by 3. What do I need to do here before I actually, attempt to recurse for both of those?
That's if it's divisible by 2 by doing a modulus
Right.
or something.
Right. Okay, so
Equals 0.
right. So if it is divisible by 2, I'm just going to go ahead and separate this call, the integer result, out into a separate variable. And I'm also going to just go ahead and take the minimum along the way. So I don't have to worry about dealing with any additional conditionals or anything like that. I'll just say whatever we got from here with doing the -1 and whatever we got from here from doing the divide by 2, we'll just take the minimum of those up until this point. So I could go ahead and store that. And it'll change if we actually match this conditional. So if we run this, we go ahead and get 4. Because making sure that everybody is paying attention, I am not necessarily seeing this information yet, or this information right here, because I haven't added the divide by 3 path. And so the optimal paths that I'm allowed are going to be basically along these 2 over here, which is a total of 1, 2, 3, 4 steps that we might have. So that is the best thing that we can do until we add the last consideration, the last thing that we can possibly do, which is to divide by 3. And then we get 3 in this particular scenario. All right. So I mentioned that this is a brute force algorithm. Anybody want to give me an idea of what they think the time complexity is of this algorithm? This exploratory sort of thing.
It's always going to have to test from every number, the number of steps from like just by subtracting 1. So it's going to do like n number of steps to get to 1 just by subtracting 1, n minus 1 number of steps. So it'd be, I think of what that works into, like n times n over 2 or something is the upper bound. And the other 2 cases, I mean, don't drive the upper bound of each round. So it's something to be on the order of n squared-ish. Or worse.
Okay. I could see how you might think about something like that based on the inputs that we're going to be given. I would say this is going to be something that might be, less on the try to reason out perspective and more so on the of just heuristics of working with multiple recursion algorithms. So Lily is mentioning n to the n. I think the n squared might be an initial good guess, but it is going to be more of an exponential algorithm instead of like a quadratic algorithm that we're working with. And the exponent itself, the exponential, is going to be dependent on the number of branches that we're going to be exploring. If you try out an example of a multiple recursive algorithm that is going to have a large enough input, oftentimes the number of nodes that you'd see in this diagram is going to be on the order of, first of all, I'll just go ahead and write exponential over here. We're going to have basically some constant, which is going to be often defining the number of branches at each level of recursion to the power of the input that we're going to be given. That's a heuristic that you should probably understand or remember, actually, really, more than anything else when it comes to recursive algorithms. And in this case, this constant is just kind of special because we don't really have a consistent number of branches at every given point. Don't worry about this. absolutely do not worry about trying to figure out the specifics of this. Just know that your base of the exponent is going to be a constant. If we had 3 branches all the time, every single time, then it would be 3 to the power of n in this case, in that case.
Okay.
Yep.
So the upper bound is 3 to the power of n, basically. So it's somewhere below that.
It's definitely going to be below that. But
Okay.
yeah, if you want to think about some upper bound, it'll never be any greater than 3 to the n.
Okay.
Okay, now let's talk about space. What are some ideas about the space complexity of this algorithm? It's going to be better than exponential. Yeah, actually, Tang, that's correct. It is going to be, in fact, O of n. Can you explain to me why? Yep, Lily, that is quite the idea. It is going to be about the maximum possible depth of recursion. So, yep, both of you have the right idea. If you drew out this tree fully, whatever is going to be in the deepest level of this diagram is going to, that length itself is going to be the maximum space that you would allocate for your program, because that's going to be the size of the recursive call stack that you're working with. So it's going to be, at worst, a scenario where we have, if I keep going, then I have 1 sitting on top. It's never going to be any larger than this. It's actually never going to be any smaller than this. I mean, it will be smaller than this, of course, but it's never going to be any larger than this. I want to just make sure that's what I'm saying. So, but this is going to be your worst case scenario that you're going to hit when you're working on this. Yeah, what is your question, Tang? Let me know whenever you're ready. Yeah, so just to make sure that this is understood about the recursive call stack, at any given time, when you're looking at all these nodes in this tree, in this diagram over here, not all of this information is going to sit on the call stack at the same time. Only like a particular, branch down the tree, only a particular depth down the tree is going to be sitting on the call stack. A number of successive calls, one after the other, along a depth. There will be other calls that will be made eventually along other depths, but they're not going to necessarily, accumulate space from other branches. It's just going to be along one branch until you go down all the branches until you hit your base case, and that's going to be the size of your space. Okay, so if there are more local variables initialized in each recursion, do they get counted into the space as well? It depends. I would say for something like that, if that's a good question. If you know that it's going to be like a constant number of variables each time, I guess you could say that. I would say I wouldn't necessarily consider that in your space complexity necessarily, in increasing your overall space. Just think about the call stack in general when you're working on something like that. If your input itself happens to scale the creation of information within each call, like for example, if there's like a multiplication of a data structure within each call itself, then you could talk about increasing the size of your space or something like that. But within each call, if you have like the same number of variables that are allocated for that particular level, it wouldn't necessarily increase the space that you're going to account for when you're defining this space complexity. So it would still be n over this case. I could have like 10 variables, and that's still just going to be 10 times n, which is going to be just n, because the constant just goes away. Yeah. Okay. So let's go ahead and scale this up a little bit so I can show you all what happens when we get to larger numbers. So 37 as an input looks okay, runs in 2 milliseconds as well. And 450. Oh, wow. That's larger than usual. That's quite a bit larger. So what can we do now? This is the time in which I'm going to start asking about how we can optimize on this approach to the problem. We've done this exploratory sort of path. We're not necessarily exploring any specific mathematical optimizations. We're just optimizing on this particular approach. How can I possibly do that? Maybe what might you see in this diagram?
I mean, basically, if you get to n-1 every time you go through, I mean, you're going to be exploring the same numbers from each number down, so multiple times. So if you can memorize that somehow or another.
Yep, that's exactly what we need to do. And just to make sure that I highlight this, just make my diagram a little bit bigger. The idea is that whenever we encounter 2, for example, I know that I'm going to return the same exact result every time I see 2 as an input into a function call. So why am I doing this work again and again and again? Same thing with 3. It's a lot of recursive calls that I can just cut out. If I happen to calculate a result for 3 at this point, I can go ahead and utilize it at this point instead of actually doing all of this work over here. So yes, the idea is that we can actually consider doing memoization to, to cut out this repetitive work that we're doing. Right, so let's just go ahead and cut this out. And what we're going to do is, let me see if I have some space. I'm going to do some form of memoization. And what that means is we're going to be caching results to repetitive subproblems as we're recursing. All right, so let's go ahead and take a copy of this. And let's create that cache. I'm going to rename this function to something else. The cache is going to be a key value pair type of system, right? It's going to look like either an object like this, dictionary hash map, whatever key value store that you can use that has an O of 1 access time when you need to use it. What we're going to do is, for a given function state, or in this case, basically the input of the function, if we happen to have seen that function state before, that particular input before, basically if it was in the cache at another time when we ran through this function call, through all those function calls that you happen to see in the tree diagram, what we'll do is just return the result that we cached for that particular input. I'm just repeatedly saying function state because your function state will not always be defined by the input into your function. It could be defined maybe by global variables or passed by reference variables where you're going to have a certain output that will be different based on whatever happens to be your state at that particular time with your function. In this case, it's simple. The only state that we need to work off of is just the input into this function because there's no global variables that we're working with. So we can just use that. Now, of course, we need to actually put entries into the cache itself. So I'm going to do that down here. I'll just take what we did and just store it in a variable, and I'll just return that, of course, just to separate it out into a variable. But I'm separating it out into a variable so I can put this result into the cache for our input. Okay, so let's go ahead and give this run after create some labels over here so we can see a difference in timing. And we run this, and there's basically 3 orders of magnitude difference in timing when we decide to use caching to store subproblem solutions. If you want an idea of how often this cache actually is used, I can create a count variable over here, and let's go ahead, store this in a variable. This will give you an idea of how many redundant recursive calls we're making typically as we go through this. So if I go ahead and give this a run, for this input that we're working with, 450, this 373 times that we happen to access this cache. And this should be a very easy indication for you that caching is going to be the way to go when it comes to knowing what information is going to appear repeatedly every single time. And that's the advantage of having a diagram, because it'll show you, okay, well, am I repeating work somewhere? Can I optimize on an exponential algorithm to actually get to something that's going to be better? And if anybody wants to know what the cache looks like too.
So is there a higher level, because I tried this exact thing in Python and I can't get up to I can get to 1,000 and it runs very fast, but if I put in 10,000, it crashes. I don't know if it's because my Jupyter notebook is running out of memory or.
Nope, not necessarily. You actually hit the next point that I am going to bring up, because memoization is going to be the easiest possible optimization that you can do on a brute force recursive algorithm that has apparent negative work, repetitive work that you're going to be dealing with. But we run into a limitation that we'll see, right? We can maybe scale up these inputs. Looks like it's going to be okay. Let me actually comment out this one over here. But of course, like you were saying, when we get to numbers that are this high, I know you said you were trying this in Jupyter, it's going to be, there's going to be an issue.
We have to make it iterative, or do we have to do a different type of memoization?
We will, in fact, actually have to do an iterative approach to this. I know some people might suggest that you can do tail call recursion, where we're cutting out recursive calls that are going to be unnecessary at a certain point. But I just want to make sure everybody understands what is the issue here, just for anybody else that might not be aware. Why is it that I might run into an error if I have this input here? This isn't very large, right? Computationally speaking.
The stack, it has a maximum stack size and it's hitting it.
Mm-hmm. Yep. And that's what's shown in the error over here. So that's the whole thing, right? If you choose to use recursion, it's fine to solve a problem in an interview, just to say okay, I understand what to do. I understand maybe some basic optimizations to do, and it gets me to an O of n solution. This is a linear solution, by the way. But of course, you'll run into the program limitations when it comes to the practical applications, where using recursion is just not the right way to go in a real world scenario. And we can start to think about how we might translate this into an iterative algorithm based on the steps that we've taken so far with the recursive algorithm. So how that's going to look like. Instead of actually working from the top down, right? I started from my higher input and I just kept building upon solutions that were provided by lower examples. Why not instead build those lower examples from the bottom up instead of starting from the top down? So this is a top-down approach that, of course, is going to run into the limitation with a call stack size, which is going to often be the case for many systems and languages. So this is top-down. Let me make sure I didn't. Okay, so what we might consider doing instead is actually a tabulation approach. What I talked about earlier with this optimization over here with memoization, it's called dynamic programming. There's another style of dynamic programming that doesn't necessarily involve using recursion. That's called tabulation. Right? Has anybody not heard about tabulation before in general?
That classically the whole knapsack problem approach that you see.
Yeah, knapsack is actually a very common problem that makes use of tabulation. Though you can definitely use memoization to solve that problem as an initial approach. but knowing the recursive relation itself allows you to actually build a tabulated solution for something like this. So Brandon, Terika, Ivan, Min, we will get into what this means to actually do this. I'm still going to be using some kind of caching data structure, but I'm going to be building it up iteratively from the bottom in a certain sense. So we're building a table of subproblem solutions. And this is going to be based on a base case. And I guess we can also say recursive relation that we came up with earlier. Right, so in this particular case, the base case that we came up with was when n is equal to 1, then we'll just return 0. The recursive relations that we said, and I'm just writing this again. We said that we will consider 1 plus the minimum of 3 different routes, right? We can choose the n minus 1, the n divided by 2, or the n divided by 3 route that we might work with. We'll do this in the context of a table. So in my table, and it could be a dictionary or a cache or hash map, whatever else you want to do. It just needs to be some kind of key value store. In this case, I'll be using, my keys will be the indices into the table, and my values will actually be the values at that particular index. So we'll say for my values in the table, it's going to be the minimum number of steps to 1. How about, hold on, steps from I to 1, right? And my indices or my keys, whatever you want to call it, is going to be I itself, which is going to range from 1 to n. So if I start writing out my table, let's write out some indices. Tables have to start at 0, so we'll deal with that even though 0 is not going to be used at all. It's just because that's just how tables work. We have to just work with it. Okay, so I have this sort of key value store that I'm working with, this table. And just say that for 0, we'll have no, we're not going to deal with it. But for 1, this is going to be where I can apply my base case. Right, so let's go ahead and, oh, not there. There we go. Go ahead and say my base case is going to be there. I'm going to have 0 for that particular case. Now let's go ahead and move on to the next value up from that. Let's see what we can find for 2. What I can do is I can take 2 minus 1. Let me write these out too. So this is going to be minus 1 divided by 2 and divided by 3. I'm just going to use colors for these. Or we could choose 2 divided by 2. And then I want to see what the result is for having that particular input in those scenarios. Well, I stored that result in a table already. That was my base case. I can take the minimum of those values, and to acknowledge that step of either choosing to subtract 1 or divide by 2, I'm going to add 1 to that. This basically looks pretty much just like what we did with the recursive approach, right? I'm choosing one of these, and then I'm adding 1 to either one of those steps. The difference is, instead of starting from 2 from the very beginning, I gave the result for 1, and then I'm going to move on to 2, and all I'm going to need is just a table reference to work with in this case, instead of making recursive calls and having to cache those values each time. So this is going to be 1 over here. Okay, and then from 3, we can either choose to take the result when we subtract 1 from 3, or we can choose to see what the result was when you choose to divide by 3. And then we can take the minimum of both of the values at that point, those points in the table, and we could add 1 to that. Okay, and that's going to give us 1, right? Because the minimum of 0 and 1 is just going to be 0, and 1 plus 0 is 1. We can keep building out the table, and as we keep doing this sort of thing, we get a completely filled out table like this. And for each point in this table, all we need to do is just look back by the possibility that we're working with. If it's divisible by 2 or divisible by 3, we will check. Otherwise, we'll just subtract 1 and see what the value is at that point. If you want to try and represent this, let's say this is going to be a sort of array-based way of representing the recursive relation. Instead, how we can say this is going to be the minimum of the table value at I minus 1, or the table value at I divided by 2, or the table value at I divided by 3. And we don't need to redo any calculations at any point at all, because we're just referring what we've already done before, making sure that we store that information so that it can be used later. Okay. Any questions on this? Oops, I didn't make my diagram fill the screen, but any questions on this particular approach?
So you could use any data structure you can use with an index. Like in Python, it might be easier to still use a dict because you don't have to initialize a list.
You could. Yeah, you definitely could. Yeah, if you wanted to. Of course, I would say with a list, if you predefine the size of the list, in a sense, that's kind of a little bit slightly more optimized than
yeah, it's a faster constant lookup, but either way, it's a constant lookup, I guess.
Well, it's not so much for the constant, but it's about dynamically increasing the size of your data.
Oh yeah, because every time it doubles it, it has to like double the internal storage.
Right.
Yeah.
But then if we predefine the size of the table, you don't have to worry about that reallocation step behind the scenes. So that's just the advantage of using like a predefined table with the size that you know about how big your data structure is going to get. And then you can just fill in the table as you go along. So we'll initialize a table or array, whatever you want it to be. And then what we'll do is apply base case to table. And then we'll loop through table filling solutions to subproblems that are going to be based on the base case. And what's the last thing that I'm going to do? What am I going to return at the very end of all of this after I built out this table?
Final result.
Right. That's sometimes people forget about that in that last part, that we want to actually return value at the end of the table itself. Because we're actually trying to build a solution for each key, each index. I have a solution for 1, for 2, for 3, 4, 5, 6, 7, 8, 9, and finally a solution for 10, which is going to be at this point. This is what I was trying to build, right? This is what I want to actually return at the end of the day. So yeah. We were already actually handling all that minimum sorts of calculations along the way. When we get to 10, just to make sure that this is apparent what we're checking the solution for 9, and we're also checking the solution for 5. And we're just taking, the minimum between these, and we're adding 1 to that, right? So the minimum between 2 and the minimum between 3, and we'll add 1 to that, which actually gets us this result that we're getting over here. So once we get to that point, we can go ahead and return that. So we return the value at the end of the table because that's what we're trying to build up to. So let's go ahead and quickly put this out. So I'm saying n plus 1 because technically we have 11 indices. And table indices have to start at 0. We just have to work with it again. But we're not going to use that first index, but it's trivial anyways. But I'm just making this so that I can say at 1, this is what I'm going to do. At 2, this is what I'm going to do. It's just kind of like my own functional need for working with something like this. So let's say for an input of 1, I should return 0. This is my base case. And let's make this a little larger. Okay. Okay, so this is going to be bound from, hold on. Okay, here we go. This would be bound from 2 up until n, up until and including n. And what I'm going to do is pretty much practically the same sets of operations that I was doing in the recursive algorithm, except instead of making recursive calls, I can just do table references instead. So the beauty of how we can deal with these top-down algorithms and transform them into bottom-up solutions like this, because at the end of the day, you are still making use of a recursive relation. You're just building all the information you need from the bottom. Okay, so I'll still have the result that's going to be the minimum of all the pathways that I might choose between either selecting the reference of -1 or the divide by 2 or the divide by 3 reference. And then I will store that value in the table itself for that particular point. And the last thing I'll do is just return the table value at n, which was my input. So, okay. Let's make this a smaller input too. Let's run this. Okay, looks like we have an input that makes sense. All right. Larger input, same output. Difference in time. The last question I'm going to ask everybody is, why is it that the memoization approach might take a little bit longer than the tabulation approach?
Is it you have to like reallocate a stack frame each time?
Yeah, so that can actually contribute a lot to what we're going to be doing, right? So with a recursive algorithm in general, you have to worry about this dynamic allocation of a stack frame that's going to be a lot of, functional information, function headers and pointers and everything, like all pointers, all that kind of stuff. Sorry if I'm like messing with some of the details about that, but you're just going to be dealing with a lot of overhead that comes with doing recursion repetitively and dynamically, and without the program necessarily knowing the stopping point of recursion unless your compiler optimizes for something like that. And alternatively, with the tabulation approach, you're predefining the size of your data structure and you're just filling in the values with just look back references, which are very simple. Okay, so, all right. So that is the min steps to one problem. These thoughts about how you might approach recursive problems that could have some optimization strategies. I know a lot of you didn't necessarily have recursion as your first thought for doing something like this. Also, just in case everybody wants it, I have provided a copy I provided a link to a copy of the code that I've just worked out of. So you can find that in the chat. Please do not edit anything in the link that I sent you, because this is a publicly accessible, runnable environment. And I'm sure a lot of people might actually find this useful to have something to refer to. So just take a copy of it and you can work with it that way. If anybody wants to take a copy of a screenshot of my diagram over here, I'm just going to go ahead and move to the second screen and you can take a screenshot of this. I'll wait for about maybe 15, 20 seconds, and then I'll move on to the other screen. Yeah, but any questions for me about this problem, about recursion, or just about Outco in general?
So you said this is a problem that Google, or I guess like those like Fang likes to ask, I guess.
Mm-hmm. Yeah, this is a kind of problem that you could possibly see. Yep. Oh, one point that I forgot to mention. Want to make sure everybody knows very clearly what we're working with. What is going to be our time and space for this approach? What am I looking at?
You have n iterations. So it's some constant. I guess it's not every single time the same number. it's on the order of n for your number of iterations. And then I guess you just look at the last one.
You guess what about the last one?
I mean, you just go through n iterations and then you look up the answers. So I guess it would be order of n.
Yep. It would definitely be order of n. I mean, technically, it's going to be some constant times n, but the constant always fades out as n tends towards infinity. You don't really care about constant multipliers. You care about the actual n order variables that we're working with. And for space, it, of course, will also be n, because we're only allocating a table that's going to be of size n, which is our, yeah, that's what we're going to be working with. Okay. All right, I'm going to move on to the first screen so we can have that as well, if you all want it. So I see, Andrew, you actually posted a solution as well. You created some table and then...
It is very, it's exactly the same thing. It's just Python. I just thought it might be useful in case somebody knows Python better.
Yeah. It's a good summarized solution.
So if I understand this correctly from the table, like say you have 100, it's going to be looking back ultimately to the table result of 10.
Possibly. That might not always, I don't know if that's going to necessarily be the particular route. You can probably find a way to track it by modifying the algorithm that we've provided. It might be easier to actually track it using a recursive approach, though.
So it's, I mean, it's just saying it's looking like recursively to like the first closest, and then the one before that, and the one before that, until it gets to, you know, our goal of 1. So that's why the table approach is very, it's how it optimizes it. I don't know if that was confusing.
Yeah, I can understand why it might be confusing. That's why, like, the whole idea behind the table approach is that we always start off with smaller examples and we build upon those smaller examples. And that's going to be important when you're thinking about working with these problems. You have to see what makes sense of the smallest examples first, because it's going to be very hard for you to visualize what would make sense for the larger examples, right? You can't visualize every single possibility of what happens between 1 and 100 unless you draw all that out. And that's going to be a lot of drawing for you. So you can make something work, but I wouldn't necessarily try to come up with some conclusions behind what would be the optimal path unless you're asked to actually define that path itself, which would actually be a bit harder with a tabulated approach. I know this was confusing, but just know that, like, for each point in this table, what it is saying is that I'm optimizing for the minimum number of steps to get from this point to 1, or from this point to 1, I'm finding whatever is overall the minimum number of steps to get to 1 from that particular point, which is going to be based on the minimum number of steps to get to this particular point.
So like, yeah, so like from 10 to from 5 to 1, you would find the minimum amount of steps you need to get to 5, and that would just also be, and then you just add on the minimum number of steps from 5 to 1.
Oh, you mean, well, it would actually be based on the minimum number of steps to 4. The minimum number of steps to 5 would actually, in fact, it would have to be based on the minimum number of steps to 4, because you can't just blindly kind of think about a result. It has to be based on a previous result that would have been calculated. So we would need to check what we got at this point, which is going to be 2, because that's the only option we can do, right? You can't divide by 2, you can't divide by 3, you can only subtract 1. So every single point in this table is dependent on a point that is further to the left of it. So that's what you need to work with. And the way that you would reason something like that is first understanding what happens if you try to do this recursively. That's why I showed you the recursive algorithm first, because that shows you that every single action that you take depends on the actions below it in the recursive tree. the results that return for each of those actions. Okay, Tang, you're asking, will the recording be given out to the participants as well? Just send an email to programswest@outco.co, and they'll be able to give you a chance to ask about those kinds of things. I can't necessarily give it to you right now because the recording has to process after this meeting is over. So just send an email there and they'll respond to you about that. And also for any other questions in general that I may not necessarily have answered in this session. Shirley, did that answer everything for you?
Oh yeah, I like just trying to get it like conceptually, just like from the scale of like if you had like numbers in the billions.
Yeah.
Like how tabulation how that would be optimized by tabulations.
You'd have a billion-sized table.
Yeah, which
that's
would
the way.
stink.
You think it would stink, but the thing is, you're creating the tightest, most guaranteed bound that you can on a working solution that isn't trying to find something like, like some really, esoteric conditional approach to the problem.
Without actually using like mathematic knowledge or something like that.
Right. Mm-hmm. Even if you did use mathematical knowledge, you're not necessarily guaranteed to find your solution. I mean, think about it. Think about like other mathematical scenarios where like, I don't know, when you're thinking about, I know this is like very different, but when you think about prime numbers, right, you can't always come up with some formula to like figure out, what primes and that you're going to be composed of, right? That's the whole point of like encryption algorithms that you'd be working with, that information is sort of obscured away, that you have to try all the possibilities that you're going to be working with for some problems.
I mean, I was like thinking, well, it would be a prime 2 to the power of like whatever billionth minus 1 would be. Wouldn't be what the prime number is gonna be. But I was thinking like with this problem, like without like creating a table of a billion values, how best to use a combination of like loops and recursion.
Well, at the end of the day, I think you might actually possibly underestimate the toll of actually using loops with recursion anyways. Doing recursion on this problem is still going to net you a space that's going to be on the same order of that billion-sized table. I know that might sound a little crazy to you, possibly, that making a table of a billion size is actually the better route to go, but it would be, because you're predefining the information that you're going to be given. And in terms of the bounds of the, isn't very large, computationally speaking.
Yeah, I'm not very familiar with like computer science and like the O notation and things like that.
That's perfectly okay. That's things to learn, things to work with. If you actually, let's see, cheat sheet, big O cheat sheet. Let's go check this out. I don't know. Am I still sharing my screen?
Yeah.
Yeah.
So
Yeah. Okay.
What's an example of a large O notation?
These are what you might be looking at. So the first algorithm that I talked about, just the purely recursive exponential algorithm, I said that it was some constant to the power of n. That's an example of a larger situation that you might deal with.
So ours was the upper bounds. Someone said it was 3 to the n.
You're never ever going to reach that scenario. That's not even really a worst case. But if you want to just have some number out there, you could say 3 to the n, but that's not necessarily going to be the right answer.
So what is like the O notation that most, I guess, engineers are trying to abide by?
Okay, so I'm going to paste a link to this in the chat, because this is what you can use to answer those kinds of questions. And
I guess like O notation, the way I think about it is like if you have a certain notation, you can, and it's like too large, you can say, okay, there's definitely a better way of solving this than this method.
Yep. And often in a lot of cases, like that is what you might end up sort of thinking, right? If you end up with a quadratic solution where you might not necessarily need to do that, right? O(n) squared type of solution. Maybe there could be optimizations for doing like n log n.
Oh, I did not see the color code. I need to learn to read.
That's okay. That's quite okay. So yeah, this could be like a good heuristic to think about, but I wouldn't just hold on to this as like the end all be all of everything, because there might be scenarios where you are just confined to having to do the worst case scenario. I'll give you an example. For example, if you, I know I'm actually discussing more than what is, what is in the scope of this, but I feel like this might be helpful for some folks. So let's say that I wanted to produce a power set of the letters A, B, and C. Right? Now all the combinations that are going to be possible with these letters. I can either have an empty string, A by itself, B, or C, or A, B, or B, C, or A, C, or A, B, C. I'm not necessarily caring about ordering. I'm just going to say that combination of letters that I'm going to be given, right? This is 3 letters that I have over here. This is 2 to the 3rd possibilities that we are producing. There is absolutely no way to avoid hitting a time complexity that is going to be this exponential component, basically 2 to the n in this particular case, because you have to produce an output set that has all these values. So there are just some algorithms where you're just going to end up with this scenario that you can't optimize any further.
What does n represent here?
N represents the string length, the input string length.
And this is not caring about order.
Yep.
Or unique to order.
It's not caring about the order of the letters. It's just that combination.
But like, would AB and BA be the same thing?
It would be the same thing.
Okay, cool.
We're just talking about combinations here. If we're talking about permutations, AB and BA would be distinct.
Mm-hmm. Okay.
Yep.
So this is basically distinct sets almost. Because the
I guess,
order doesn't matter. Okay.
Yep. You can say something like that, yeah. Yeah. Okay. All right. I wanted to sort of bring some things back. Of course, there was that email that I provided you all with. I'm just going to paste it again if you have any additional questions and about the program in particular. And if you are curious about applying, I'm also putting a link in the chat as well. You can just click on the apply link and we'll send you over a fundamentals check test of some kind and see where you stand and we can move on from there. If you don't pass the fundamentals check, again, actually not again, if you don't pass it, that's okay. It's not going to be as difficult as what the problem was that we discussed today, but it'll be simpler. You could just take a chance to study up on some algorithm materials that we'll provide, and then you can retake the test again. We're not very strict about just denying people. We just want to make sure that everybody is on sort of a similar level of sorts as we move through the material of the program. Yep, sure, Andrew. Go ahead and head out as you need to.
I feel like this problem is so not real world applicable.
Are we talking about the min steps to one?
Just algorithms in general, like when you're working.
They're not always going to be applicable. But the thing is, walking through them in your interviews is going to be part of your, being able to discuss your problem solving process is just what gets you through these interviews. It's just kind of an unfortunate reality of software engineering interviews.
The luck of you actually being familiar with the problem. Like if you've practiced a similar problem or the same problem, and that's the problem they use to test.
I'd say it's probably more than that, right? There's a lot of problems that share, there's a lot of tools that you need to have underneath your belt, like common problem solving tools when it comes to algorithms. Even if the problem is not like familiar to you, maybe there's an element of it that you could just use something out of your toolbox to actually solve that problem itself. You know, like, yes, you might have more luck if the problem seems like something that you've seen before, but that's not necessarily going to be the interviewer's gauge on your ability. As a matter of fact, if you don't say, hey, I've seen this problem before, and you just run through it like, oh, wow, this is magic, I know what to do. then they're not going to be able to assess your problem solving ability, and they're going to know, because they've given the test to people 1,000 times possibly from the same test bank, that you're going to be one of those people that knew what to do and wasn't honest about it. Yeah, so yep. I'm not going to say it's impossible. I'm not going to say it's all about just knowing specific problems. So a lot of pattern recognition, and that does take practice.
I find building a React app much easier than
It might be. It might be. It might be. Okay. All right. We are running at 10 minutes past the hour. It's been a while. Is this program useful for JR devs? JR, I'm sorry. Can you tell me the acronym that you're trying to say? Junior devs. Yes, this often would be useful for junior devs. One thing that I will say, just as a caveat in general for anybody, regardless of whether you go through this program or not, we are in a landscape right now where getting hired as a junior dev is going to be more difficult. And that is pretty much the case even when it's not COVID times. It's just that it's a catch-22 of applying to job application or job positions in general. You need to have experience to get a job. You don't have experience for jobs that, might be junior ones. But yes, it is often going to be useful for folks that are maybe bootcamp grads or fresh grads still.
Do you guys provide career counseling?
Absolutely. This tech class was just an example of what a tech class would look like.
Mm-hmm.
But we have career classes that run alongside as well. And they go through revamping your resume, all the things that you need to focus on from, sort of a STAR perspective, situation, task, action, result, that kind of thing. And also with regards to how you approach your behavioral interview questions. So it's not just about the tech stuff. Yeah, of course, Lily. Of course. That's quite a morbid thing for you to say, Brandon. Yeah. Yeah, it's the interesting thing about there's so many, everybody talks about there being like this plethora of roles out there for developers and this shortage of developers to actually employ for the roles. But, employers are stingy about who they're choosing to employ, even though a lot of you who are choosing to come to this session are more than capable of actually passing these interviews, right? You're trying to do something to forge your career. You're not just doing this for no reason. So there's a lot of ways that you can navigate that kind of thing. Yep. Yeah. Junior positions have disappeared a lot in these times, but it's not impossible. I'll tell you that much. That's the kind of things that we sort of try to help you along with. So even if you go through the program and, you don't necessarily get a job during the program itself, that we do have ongoing sessions that happen during and after the program, like office hours sessions, mock interview practice sessions for you to interview with other peers that just keep going on until you actually get a job. We also have a threshold that we require, the effort that you should put in with regards to how much you actually reach out to companies and put in applications, that sort of thing. All right, I did a lot of talking. 9 of you are still left over here. You all are champions. Of course. All right, I'm gonna go ahead and let you go. I hope you all have a wonderful evening. Take care.
Is it too late to ask a question?
Yeah, sure. What did you have in mind?
I asked earlier in the chat, so I saw on the website that the application deadline was November 9, but I believe the Founders Day was today, so I'm not sure if I'm looking at the right place.
You're talking about the deadlines for, or like the start date for the next session? Is that what you're asking?
Yeah.
Or let me see. When is going to be the next one? The reason why the schedule is like a little bit strange right now is that the last week of November and the last couple of weeks of December, we don't necessarily host classes because there's a lot of people that go on holidays during those times, and it's just most conducive for us to just defer those times. So just go ahead and put in your application. You may not necessarily start on the next one. Are you trying to apply for the Eastern time zone class or the Pacific time zone class?
I think I'm going for the Eastern time zone.
Okay. Yeah, I think we just need to update this information on our site. The next class is probably that you could probably apply to is probably going to be later than the 16th, but you can still try. Sometimes we fast track applications and get them in within like a 3 to 5 day period or something like that.
Right. I see. Thank you so much.
Okay. See you all. Take care.
Bye.